Glass, a versatile and ubiquitous material, has ancient origins dating back thousands of years. The journey of glassmaking begins with sand, specifically silica sand, which is rich in silicon dioxide, silicon oxide. Silica sand is the primary raw material required to create glass, and it has been utilized since the earliest civilizations. The Egyptians and Mesopotamians are known to have been among the first to craft glass objects, and over time, the process of turning sand into glass has evolved into a sophisticated and precise art. The process starts by selecting the right kind of sand. Pure silica sand, free of impurities like iron oxides, is ideal for producing high-quality, clear glass. This type of sand can be found in abundance in various regions across the globe, including beaches, riverbeds, and deserts. It's not just any sand that can be used, though. The silica content must be high, around 95% or more, and the grains must be fine and uniform in size to ensure a smooth final product. Ancient glassmakers learned to mix sand with other substances such as soda ash, sodium carbonate, and limestone, calcium carbonate, creating a compound that would melt at a lower temperature and form glass more efficiently. This early understanding of chemical reactions laid the foundation for modern glass production. Although the tools and techniques have advanced significantly, the basic principles of melting sand to form glass remain unchanged, rooted in the same natural processes that have been harnessed by humanity for millennia. To transform sand into glass, we must first understand the scientific process behind it. Glass is formed through a process called vitrification, where raw materials like sand are heated to such high temperatures that they melt and fuse together into a smooth, non-crystalline solid. In technical terms, glass is an amorphous solid, meaning that it does not have a regular atomic structure like crystals but instead forms a rigid, disordered state. The key to making glass lies in raising the temperature of silica to around 1700 degrees Celsius, 3090 degrees Fahrenheit, its melting point. At this extreme heat, the rigid structure of silicon dioxide begins to break down, turning into a viscous, molten form. However, pure silica requires even higher temperatures to melt efficiently. This is where fluxes, such as soda ash, sodium carbonate, play a crucial role. Soda ash lowers the melting point of silica to a more manageable level, around 1000 degrees Celsius to 1300 degrees Celsius, 1832 degrees Fahrenheit to 2372 degrees Fahrenheit, making the process more energy efficient. When soda ash and limestone are added to the mix, they also improve the durability and workability of the glass. The soda acts as a flux to reduce the melting temperature, while the limestone helps stabilize the molten glass, preventing it from dissolving in water. The result is a more stable and long-lasting glass, suitable for everything from windows to drinking vessels. The heating process is done in a furnace that can maintain these high temperatures consistently. Once the mixture melts, the molten glass is shaped into sheets, containers, or other desired forms. As it cools, the amorphous structure remains locked in place, resulting in the solid, transparent material we recognize as glass. This delicate balance between temperature, time, and composition is what allows glassmakers to produce a wide variety of products, from thin sheets for windows to intricate glass sculptures. In modern times, the glassmaking process has been industrialized, allowing for large-scale production of glass for a multitude of uses. The most common industrial process for making flat glass, used in windows and mirrors, is called the float glass method, developed in the 1950s by Sir Alistair Pilkington. This method revolutionized the glass industry by producing perfectly smooth, flat glass without the need for polishing or grinding. The process begins by feeding silica sand, soda ash, and limestone into a furnace where they are heated to form molten glass. The molten glass is then poured onto a bed of molten tin, a metal with a higher density than glass, allowing the glass to float on its surface. As the molten glass floats on the tin, it spreads out evenly and forms a smooth, flat surface. The glass cools slowly as it moves across the tin bath, and by the time it reaches the end of the line, it has solidified into a flat sheet of uniform thickness. This float glass process is highly efficient and capable of producing vast quantities of glass with minimal defects. It is used to create everything from window panes and mirrors to automotive glass and solar panels. By precisely controlling the temperature and composition of the glass mixture, manufacturers can create glass with specific properties, such as increased strength, heat resistance, or insulation. Another important modern method is the blow and blow technique, used to create glass bottles and containers. In this process, molten glass is first gathered and shaped into a small hollow parison using air pressure. This parison is then blown into a mold to form the final shape of the container. Automated machinery has greatly increased the speed and precision of this method, allowing factories to produce millions of bottles and jars each day. While industrial methods dominate glass production, the ancient art of hand-blown glassmaking continues to thrive among artisans who value craftsmanship and creativity. The process of glassblowing, practiced for over 2,000 years, involves heating glass to a molten state and then shaping it by blowing air into it through a long, hollow tube. The resulting bubble of glass can be manipulated and expanded to create a wide range of intricate shapes. Glassblowing requires skill, patience, and an understanding of the material's behavior at different temperatures. The glassblower starts by gathering a blob of molten glass, known as a gather, on the end of the blowpipe. By carefully controlling their breath and using specialized tools to pinch, pull, and shape the glass, the artisan can create everything from delicate vases and bowls to elaborate sculptures. The cooling process, known as annealing, is critical to the success of handmade glass. Once the desired shape is achieved, the piece is placed in an annealing oven where it cools slowly over several hours. If the glass cools too quickly, it can develop stress fractures and break easily. By controlling the cooling process, glassmakers ensure that their creations are both beautiful and durable. Hand-blown glass is highly valued for its uniqueness and artistic quality. Each piece is a one-of-a-kind creation, shaped by the glassblower's hands and breath. Though the process is labor-intensive and time-consuming, it allows for a level of creativity and personalization that cannot be achieved through industrial methods. Glass artists today continue to experiment with colors, textures, and techniques, pushing the boundaries of what can be achieved with molten glass. As with many industrial processes, glassmaking has an environmental impact. The production of glass requires significant amounts of energy, both to melt the raw materials and to power the machinery used in industrial facilities. Historically, coal-fired furnaces were used to reach the high temperatures needed for glass production, but today many manufacturers have switched to cleaner energy sources like natural gas or electric furnaces. One of the key environmental concerns associated with glass production is the release of carbon dioxide and other greenhouse gases during the melting process. In response, the glass industry is exploring ways to reduce its carbon footprint, including improving energy efficiency, recycling glass, and developing new methods for producing glass at lower temperatures. Recycling glass is one of the most effective ways to reduce the environmental impact of glass production. Unlike plastic, which degrades in quality when recycled, glass can be melted down and reformed indefinitely without losing its structural integrity. This means that recycled glass can be used to make new glass products with minimal waste. Many countries now have well-established glass recycling programs, and recycled glass, known as cullet, is commonly used in the production of new bottles, jars, and windows. Looking to the future, advancements in technology may offer new solutions to some of the challenges facing the glass industry. Researchers are experimenting with new types of glass that are lighter, stronger, and more energy efficient to produce. Innovations such as smart glass, which can change its properties in response to environmental conditions, and solar glass, which can generate electricity, are expanding the potential uses of this ancient material. While the basic principles of turning sand into glass have remained unchanged for millennia, the future of glassmaking promises to be one of continued innovation and sustainability, ensuring that glass remains a vital part of modern life for centuries to come. While the basic ingredients of glass, sand, soda ash, and limestone form the foundation, many additional materials can be introduced to enhance or modify its properties. These additives give glass specific colors, textures, strengths, and other attributes. The process of introducing these additives into the glass mixture has been a crucial part of glass making throughout history, allowing artisans and manufacturers to tailor glass for various uses. One of the most well-known additives is iron oxide, which can give glass a green or brownish tint depending on its concentration. This is commonly seen in beer bottles and other glass containers. Cobalt oxide, on the other hand, is used to create a deep blue color, which is often featured in decorative glassware. For a red hue, gold chloride or selenium is added, while chromium can produce an emerald green. In addition to coloring agents, other additives can enhance the physical properties of the glass. Aluminum oxide, is often added to increase the glass's durability and resistance to scratching. Boron oxide is introduced in borosilicate glass, commonly known as Pyrex, to make it more resistant to thermal shock, allowing it to withstand extreme changes in temperature without cracking. In modern glassmaking, additives have also played a critical role in developing new types of glass, such as tempered glass, which is strengthened by controlled heating and cooling processes. This type of glass is used in automobile windows and safety applications because it shatters into small, less dangerous pieces when broken. The role of additives in glassmaking shows the material's adaptability, as manufacturers and artisans continue to push the limits of what glass can do. Whether it's making the glass more resilient, aesthetically striking, or technologically advanced, additives play a key role in modern glassmaking. Glass has come a long way from its humble origins as a functional material for containers and tools. Over the centuries, it has evolved into a key component in architecture, symbolizing transparency, openness, and modernity. This chapter delves into the historical and contemporary uses of glass in architectural designs and how advancements in glass technology have revolutionized construction. In ancient times, glass was a luxury item, often reserved for decorative purposes or religious buildings. Stained glass windows, for example, were a hallmark of Gothic cathedrals, casting colorful light into churches and creating an ethereal atmosphere. These windows were created by combining molten glass with metal oxides for color, then cutting the glass into pieces and assembling them into intricate designs. The use of glass in architecture truly took off during the 20th century with the invention of reinforced and tempered glass, which allowed for much larger and more complex glass structures. The introduction of skyscrapers with glass curtain walls, such as the United Nations headquarters in New York or the Willis Tower in Chicago, redefined urban landscapes, showcasing the strength and transparency of glass as a building material. Today, architectural glass is not just a visual element. It plays a functional role in energy efficiency, insulation, and even environmental impact. Innovations such as low emissivity, low-E, glass, which reflects heat back into buildings in winter and blocks it in summer, are essential for sustainable building designs. The use of smart glass, which can change its transparency with the touch of a button, allows architects to create dynamic spaces that adjust to lighting and privacy needs. In short, glass has transformed from a decorative element into a structural one, shaping both ancient temples and futuristic skyscrapers. As technologies continue to improve, the role of glass in architecture will only expand, making it a vital part of both design and functionality in modern buildings. Beyond its architectural and artistic uses, glass plays a critical role in science and technology, revolutionizing industries ranging from telecommunications to medicine. Its versatility and unique properties, such as transparency, heat resistance, and chemical stability, have made glass an indispensable material for scientific advancements. One of the most significant applications of glass in modern technology is in fiber optics. Fiber optic cables, made from highly purified glass, are capable of transmitting data at incredible speeds by using light signals. These cables form the backbone of modern communication systems, enabling high-speed internet, television, and telephone services worldwide. The clarity and precision of the glass used in fiber optics ensure that information can travel long distances without significant loss of signal. In the realm of medicine, glass has become essential in developing microscopes and other diagnostic tools. The ability to produce optical-grade glass with unparalleled clarity allows scientists to observe cells, bacteria, and viruses at microscopic levels, contributing to breakthroughs in biology and healthcare. Glass also plays a critical role in laboratory equipment, such as beakers and test tubes, which must withstand high temperatures and corrosive chemicals without reacting or breaking. Additionally, glass has paved the way for new innovations in renewable energy. Solar panels rely on glass to protect delicate photovoltaic cells from the elements while allowing sunlight to pass through and generate electricity. Researchers are also experimenting with transparent solar glass, which could turn windows into energy-generating surfaces. The future of glass in technology seems limitless, with ongoing research into new forms of glass, such as ultra-thin glass for foldable smartphones and flexible displays. These advancements highlight the critical role that glass continues to play in pushing the boundaries of scientific discovery and technological innovation. As with many industries, glass production faces challenges related to environmental sustainability. While glass is a highly recyclable material, the energy required to produce it, due to the high melting point of silica, has a significant carbon footprint. This chapter explores the environmental impact of glassmaking and the steps being taken to minimize its ecological effects. One of the primary concerns in glass production is the emission of carbon dioxide and other greenhouse gases during the melting process. Traditional glass furnaces, often powered by fossil fuels, contribute to air pollution and climate change. In recent years, however, the industry has begun exploring alternatives to reduce energy consumption, such as using electric or hybrid furnaces that rely on cleaner energy sources, including wind, solar, and hydroelectric power. Another key initiative in making glass production more sustainable is the use of recycled glass, also known as cullet. Recycling glass not only reduces the need for raw materials like sand but also lowers the energy required for melting. In many cases, using cullet can decrease energy consumption by up to 30%. The production of recycled glass has grown in popularity, especially in regions with established recycling systems. Glass manufacturers are also investigating ways to produce glass at lower temperatures through the use of new chemical additives and innovative techniques. The goal is to create energy-efficient processes that retain the quality and durability of traditional glass while minimizing environmental impact. Sustainability efforts are also focused on reducing water usage, minimizing waste, and cutting down on harmful byproducts in glass manufacturing plants. By adopting more eco-friendly practices, the glass industry is working toward reducing its environmental footprint and ensuring that glass remains a sustainable material for future generations. The future of glass is brimming with possibilities, driven by ongoing advancements in technology, design, and sustainability. As the demand for more efficient and versatile materials grows, glass is being reimagined in ways that extend far beyond its traditional roles. One of the most exciting innovations in the world of glass is the development of transparent electronics. Researchers are exploring the use of glass in creating transparent circuits, which could lead to the creation of see-through computers, smartphones, and even TVs. This technology has the potential to revolutionize consumer electronics by offering sleek, futuristic designs that integrate seamlessly into everyday environments. Another area of exploration is bioactive glass, which is used in medicine to support bone regeneration and healing. This glass can bond with living tissues and is being used to treat bone fractures, dental issues, and even wound healing. The material's ability to support tissue growth opens new possibilities in medical treatments, and ongoing research may unlock further applications in regenerative medicine. In the realm of construction, smart glass technologies are rapidly advancing. These include self-cleaning glass, which uses sunlight to break down dirt and grime, and electrochromic glass, which can change its tint to block or allow light. Such innovations are enhancing energy efficiency and sustainability in buildings, helping to reduce cooling and heating costs while providing dynamic, adaptable environments. Furthermore, scientists are working on new glass composites that are stronger, lighter, and more resistant to damage. This includes flexible glass that can bend without breaking, opening up new possibilities for architectural designs and consumer products. As research continues, we can expect glass to play a central role in solving some of the most pressing technological and environmental challenges of the 21st century. The story of glass is far from over. From ancient artisans crafting delicate vessels to modern scientists developing cutting-edge materials, glass has evolved alongside humanity, and its future is as bright and transparent as the material itself.